We will begin by recalling some information about the distribution of our regression parameters. Note that beta 0 hat is y bar minus beta 1 hat x bar, and beta 1 hat is s sub xy over s sub xx. What's important here is that both of them are functions of y bar, and in fact are really just linear combinations of y bar. And since any linear combination of a normal random variable is itself normal, we can say that beta sub 0 hat and beta 1 hat are also normal random variables. The mean of beta sub 0 hat we know is beta 0 because it's unbiased. And last time we showed that the variance was c sub 0, 0 sigma squared. And then because beta 1 hat is unbiased, its mean is beta 1, and we showed previously that the variance is c sub 1, 1 sigma squared. So both beta sub 0 hat and beta 1 hat have a normal distribution. So what we would like to do is run a hypothesis test for each of those betas. So our null hypothesis would be that beta I, whether that's beta naught or beta 1, is equal to some known parameter beta sub I 0. And the alternative that we're going to consider is that beta sub I is not equal to beta sub I 0. Now, the natural test statistic should be, since beta sub I hat has a normal distribution, would be that I would subtract beta sub I naught, beta sub I 0, and I would divide by the variance of beta sub I, which is, the standard deviation of beta sub I, which is c sub I times sigma. And that makes sense as our test statistic. But the problem is that we do not know sigma. So we're going to have to estimate sigma using a sample standard deviation. And so we should instead use the t-statistic, b sub I hat minus beta I 0 divided by the square root of c sub I times s. And in this case, our degrees of freedom is actually going to be n minus 2. The rejection region is going to be the absolute value of t greater than t sub alpha over 2, just like it has been for any of our other t-tests. And then the confidence interval for each beta sub I would be beta sub I hat plus or minus t sub alpha over 2, and then times the square root of c sub I times s.